Okay, so we're doing an exam review. This is the actual exam for 107. I'm going to go through and we'll talk through the solution to this exam, and we'll talk about each of these problems. So in question one, let me zoom in a little bit. Okay, is everyone able to see the screen okay and see the questions? Okay. You can also pull up the exam in the review segment of Canvas. So if you click on the exam and you hit review, it'll show you all the questions as well. Okay, so we're asked to classify the following as a physical or a chemical change. Let me break out the annotate feature. The annotation won't be as clean since it's not in OneNote, but the benefit of that is that we can directly look at what you'd see on Canvas. So we're looking for a physical or chemical change. So copper metal is melted, okay? Melting. So we're going from the solid to the liquid phase. What do we call that? What do we call that process? What do we call that process? Solid to liquid, melting. Phase changes. Are phase changes chemical or physical? So this is a phase change.
Physical.
Yep, exactly right. So this phase change would be a physical change. Does this first question make sense? Does this first question make sense?
And then it says cast into a mold.
Yeah, that's just pouring the liquid into a mold so that when it solidifies, the solid has a defined shape. The main keyword that we're looking for is just the melted, as that's a key physical change, as it does not actually change the chemical composition of copper. Does that make sense?
Yes.
Perfect. So let's look at this next case. So in question 2, we're asked to classify the following as a physical or chemical change. So zinc metal is placed in hydrochloric acid. The solution bubbles and a solution of zinc chloride is formed. So there are two keywords in this case, bubbles and zinc chloride. Did we change our chemical composition? Is zinc the same thing as zinc chloride? Did we undergo a change in chemical composition?
Yes.
Yes, so this would be a chemical change. Does that make sense?
Yes.
The bubbles also are a key hallmark that we are making a product. Remember, bubbles, generation of gas, is another one of our textbook indicators that we have a chemical reaction or chemical change. Does that make sense?
Yes.
Perfect. So let's clear this. And let's look at the next problem. So in question 3, we're given that a solution of concentrated hydrochloric acid is added to water, a dilute solution is formed, and the solution warms. So what do we call when we add something to water, when we mix something? What property are we concerned with here? When we mix something to make a solution?
Solubility.
Yep, exactly right, solubility. And as a result, is solubility and dissolving, is that a physical or chemical change?
Physical.
Yep, exactly right. It's a physical change. Perfect.
But it says the solution warms.
Yes, that can happen in some physical changes. Just like, for example, when during melting or during condensation, heat is absorbed or released. The key thing to look out for is the fact that this is fundamentally a process based on solubility And if you look at the formula doesn't change. Does that make sense?
Yes.
For a physical change, the chemical formula and chemical composition does not change. Let's look at question 4 now, and let's look at a physical or chemical property. So noble gases are gases at room temperature. So physical state, can we observe something's physical state? Can we observe something as a solid, a liquid, or a gas without changing its composition? If, for example, if you look at the glass of water or whatever on your desk, you can say and you can observe that the water is a liquid without changing its chemical identity, right? So then, is physical state a physical or chemical property? Is physical state a physical or chemical property?
Physical.
Physical, yep, exactly. Does that make sense? Perfect, perfect. So let's look at this next example. And in this case, we're asked to classify this property as a physical or chemical property, where it says noble gases are relatively unreactive. So reactivity, what does that word reactivity signal? Is that chemical or physical? When we talk about reactions.
Chemical.
Chemical, exactly right. Anything that concerns reactivity and chemical reactions is a chemical property. Does that make sense to everyone? Perfect. And if you have any questions, don't be shy to stop me. This review is mainly for everyone to be on the same page, to be comfortable with the material, because we're going to build on it in later portions of the class. Okay, let's classify the following as a physical or chemical property. Fluorine reacts violently with many metals and organic compounds. So we see this keyword once again, reacts violently. That's a chemical chain. That's a chemical property, 100%. It concerns chemical reactions. Does this make sense so far?
Yes.
Perfect. And a lot of these questions are either duplicates or variants of the homework and quiz questions. So I always try to make sure that assignments have inherent value for completing them in terms of scoring well on the summative assessments. Okay, so we're asked to classify the following as a homogeneous, heterogeneous mixture, or a pure substance. So aqueous, this is a little bit of a tricky designation. Aqueous states it's dissolved in water. So if we have something dissolved in water, is that a mixture? And what type of mixture is it? If it is a mixture. If it's something's dissolved in water.
Homogeneous mixture.
Yep, exactly right. It would be a homogeneous mixture, because we have hydrochloric acid and water mixed together to make a miscible solution of consistent composition. Does that make sense? Perfect. So let's look at the next case. So we're looking at nitrogen. So nitrogen, is that a mixture or a pure substance? Just
Pure substance.
Yep, exactly right. We only have one unique chemical formula as part of this pure substance. Okay, let's look at this next case. So we have silver chloride solid in H2O liquid. So just drawing a picture, we have our silver chloride and we have our water. So as you notice, we have two different state symbols. So then, do we have a consistent composition in this mixture? Is it homogeneous or heterogeneous?
Heterogeneous.
Heterogeneous, exactly right. And the key giveaway is that we have different state symbols. Different state symbols, separation of phases, different composition. Do these examples make sense to everyone? Everyone comfortable so far?
Magnesium strips. Okay, nothing. Never mind.
Maybe we'll get to that question. Or I'm not. Let's keep going and let's see if we encounter that question. Or if that's a separate question, I'd be happy to pull up the whiteboard and answer that as well. So we're asked to classify the following as a compound, element, or mixture, a substance that cannot be chemically decomposed into a unique pure element. What is this the definition for?
Element.
Yep, exactly right. An element cannot be decomposed into a simpler, pure element.
Professor, this is not compound? Isn't it carbon monoxide?
We're looking at 10.
Oh, 10. Okay, sorry. I was one ahead.
Yes. We'll get to 11
Okay,
momentarily.
got it.
But for our question 10, this definition is the definition for an element. Yes, I heard someone had a question. Please go ahead.
What's the difference between so for that I put mixture because so what would be the key?
So a mixture is defined as two or more pure substances that are mixed, but a mixture, it contains two or more pure substances that are not chemically bonded. You can actually take a mixture and if you process it, separate its components and then decompose its components, you can separate a mixture and decompose a mixture through chemical means into pure elements, just like you can a compound. A mixture is a combination of pure substances, which in many cases involves a combination of compounds that are not chemically bonded together. While in an element's case, no matter how hard you try for an element, you cannot chemically decompose an element into a simpler element.
Okay.
Does that make sense?
Yeah, thank you.
Perfect. A mixture can be separated into its component pure substances, but those component pure substances are not necessarily the simplest elements. They could be compounds, etc. Does that make sense?
Yes, thank you.
Perfect. So let's look at question 11, CO. I see two element symbols, 1 and 2. So then, if we have two unique element symbols, what would we call this?
Compound.
Yep, exactly right. So this would be a compound. We have two or more atoms of different elements chemically bonded together. Okay, let's look at this next example. So this one, we have a sample containing nitrogen, oxygen, and argon. And I said these components can be successively separated by cooling the sample. So what does this remind us of? A mixture, an element, or a compound?
Mixture.
A mixture, yep. And the key thing is that they can be separated through a physical process. The nitrogen, oxygen, and argon are not chemically bonded together. Does that make sense?
Professor, instead of cooling, if we would say by heating, then that would be.
That would also be a mixture. The only case where it would be a compound is where you can say the nitrogen, oxygen, argon can be separated by chemical decomposition.
Okay.
Yep. Compounds, they're chemically bonded together. So you need to use chemical means to separate the elements in a compound. For mixtures, since the components are not chemically bonded, you can use physical means like heating, cooling, etc. Does that make sense?
It does. Thank you.
Perfect.
How do we know it's chemically bonded?
So the key signpost, if they're chemically bonded, you would not be able to separate the nitrogen and oxygen and argon easily via physical means. Additionally, you can know that they're chemically bonded because that compound, the components in that compound would not be easily separable. Does that make sense?
Yes.
Perfect. And finally, for question 13, this one's a bit of a freebie and a nice easy one. Is carbon an element, compound, or a mixture?
Element.
Yep, exactly right. Perfect. Okay, so let's clear out our drawings and now let's discuss this next example. Okay, so we're asked to fill in the blanks. So we're given the symbol for sulfur. So we're given the symbol. And we're asked to fill in the blanks in this table. So S corresponds to sulfur. What is the state of sulfur at room temperature? What is the physical state for sulfur?
Solid.
Solid.
Yep, exactly right. The chemical formula, sulfur is a polyatomic element. And what's the formula?
S8.
S8.
Yep, S8, exactly right. Sulfur, as we know, is a non-metal. What is the period number for sulfur? What is the row that sulfur is present?
3.
Yep, exactly right. And looking at the periodic table, looking at the entry for sulfur, what is the atomic number for sulfur?
16.
16, exactly right. So now we need the family name, family number, and the number would be 6A or 6. Either would be accepted. Now, you can also call this the chalcogens, but I didn't discuss that in class. So if you put it, I'd give you credit for it, but that's not a very commonly used name for the 6A elements. Does that make sense to everyone? Does this
Yeah.
make sense?
Professor, so I I thought non-metal would be like because it was categorized in not as a non-metal.
Yes. Oh,
Is
so,
that
sorry? For non-metal for what? For what?
for
category?
for sulfur?
Yes. But
Okay.
which category are you talking?
The atomic number, family name, or family number. I thought it was just the family name was considered like non-metal if we didn't put 6A.
The family name is the group name or number.
Okay.
Mhm.
If
If you
we
put-
don't memorize it's S8, then how do we figure out the chemical formula?
That you'd have to know. You could also try drawing a Lewis structure, but for the elements, that's part of why I went over these common chemical formulas, because we're going to be using these formulas in the chemical reactions chapter. So I always like to test on the skills that we need in order to have less difficulty in later parts of the class. So I wanted to make sure everyone was familiar with the formulas of common elements. So that way, when we start writing out chemical equations, balancing chemical equations, we don't have as much trouble with the formula. Does that make sense?
Yes, yes.
Perfect. Any other questions? And yes, you can put group 6A, that's more than okay. Okay, so let's look at the next case. So for question 15, we're asked to play a fill in the blank game. It doesn't seem like we have a lot of information, but in reality, we have all that we need. We know that it's a liquid and it's a non-metal. So what non-metal is a liquid at room temperature?
Bromine.
Bromine, yep, exactly right. So the name would be bromine. And considering that bromine is a halogen or a 7A element, what is the formula of a halogen? Are these monoatomic, diatomic, or polyatomic?
Diatomic.
Diatomic. So the formula would be Br2. Does that make sense?
Professor, like for example, for this one, I put Br2 parentheses L for liquid.
That would be
And then
okay.
it deduct the number from me, so it didn't give me the right the point.
Yeah, I'm still going through and correcting the Canvas automatic grading. I make sure to
Okay,
grade
great.
all the exams by hand. So I'm still processing that, and the final scores after I've gone through everything by hand should be uploaded soon. I'm still working through it to make sure everything's correct, and grading the parts that I have to grade by hand. But yes, if you put Br2 liquid, that's more than okay.
But in general, just forget about the exam. When they ask us, should we put the state or we just put it when we are writing the equation? Like the state of
You can
the.
put that for the formula. That's more than okay.
Okay, thank you.
So looking at the period number, so if we look at bromine in the periodic table, what row is bromine found in?
4.
Yep, perfect. So the period number would be 4. And then looking at bromine's panel, the atomic number or the number above bromine is 35. Does this make sense to everyone?
Yes.
Perfect. So let's keep going now, and let's look at question 16. So we're asked to fill in the following table, and we're given that we have a solid non-metal that is group 5A. Solid non-metal group 5A.
Phosphorus.
Phosphorus, exactly right. So we'd write the name. The chemical formula of phosphorus. What is the formula of phosphorus?
P4.
Yep, it's a polyatomic of the form P4. Looking up phosphorus in the periodic table, what row is phosphorus present?
3.
3.
Yep, exactly right. So it's in the 3rd period. And if we look up the atomic number for phosphorus, we would see an atomic number of 15. Does this make sense to everyone so far?
Yes.
Perfect. So let's look at the next example. So we're asked to fill in the following table when we're given that we have a halogen, which is a 7A element, with a period number of 2. So what element is that? A period 2 halogen.
Fluorine.
So in the 2nd row and the 7th column, that would be fluorine. Halogens, as we discussed, are diatomic species. And what is the physical state of fluorine? Is it a solid, liquid, or gas?
Yes.
It's a gas. Now, as fluorine is a halogen, it would be classified as a non-metal. And looking up fluorine in the periodic table, what is fluorine's atomic number?
9.
9.
9, exactly right. There we go. So we've completed the table for fluorine. Does that make sense? Perfect. So let's discuss the next part. So looking at this next example, we're given that we have an atomic number of 11. What element in the periodic table has an atomic number of 11?
Sodium.
Sodium, yep, exactly right. So the symbol is Na, the name is sodium. So what is the physical state? What is the physical state of sodium at
Solid.
It's a solid. Yep. Sodium is clearly a metal, and its group number is 1A. It's also known as an alkali metal. And that's why knowing the group names is pretty important, because it tells us immediately we have a metal. Okay, now are metals typically atomic, diatomic, or polyatomic? Are they typically atomic, diatomic, or polyatomic?
Atomic.
Atomic. So the formula would just be sodium. Does that make sense to everyone?
Yes.
Perfect. Now for the period number, sodium, looking at the periodic table, is in the third row. Okay, perfect. So let's look at this next example. For the sixth row, iron, we're to fill in the following blanks. So Fe, that corresponds to iron. Iron So we have the name iron. Iron is most clearly a metal. As such, its physical state would be solid, and we'd write the formula for an atomic species. Now, thinking about iron, what is iron's atomic number? What is iron's atomic number?
26.
26, exactly right. And what row is iron present in?
4.
4, yep. So we're in period 4. Now, the group number for iron, if we look in the periodic table, is 8b. You just read that off from the column. Does that make sense?
Yeah, Professor. So what would be I thought like transition metals were family names.
So transition metal refers to a region or block in the periodic table, while the group number or family name is more specific. It's the column number or name.
Oh.
Does that make sense?
Yeah, I thought that was just the family name. Oh man. Okay.
No problem, no problem.
Thank you.
Professor, same thing for here. I put 8B and then it says it marked wrong. I have no idea why.
I'm gonna go through and check it by hand, so don't worry about that. Sometimes Canvas is very particular about how it wants things formatted, but I do like having free response questions since they're a little more developmental, in my opinion, than multiple choice, which can sometimes give pretty random distributions. But yes, I'll take a look, and I'm still going through and grading these by hand, just like any normal exam. So don't worry about that.
Thank you. Yeah, when I saw the grade, I knew you didn't grade it, some of the uploaded one. I just freaked out. I was like, oh my God, it can't be. And then when I went one by one, I saw
it only shows the preliminary, the things that Canvas was able to score. But of course,
Okay,
I'm looking through and scoring the rest of them. So, Okay, so let's look at the next example in this series. So which two elements in the table would have similar properties and reactivity? And when we say similar properties and reactivity, we are looking for the same group. So what two elements are in the same group?
Bromine and fluorine.
Yep, exactly right. So bromine and fluorine, we would expect that they would have similar properties and reactivity. Does that make sense? Okay, so let's keep going with this. And let's fill out the following table. This is isotope notation. So looking at selenium, so we have selenium 74. So we know the mass number is equal to 74. If we look up selenium in the periodic table, what is our atomic number equal to?
34.
34. Okay, so our atomic number is 34. Ergo, our number of protons is 34. For our number of neutrons, all we have to do is take the mass number minus the number of protons, and that gives us, for our number of neutrons, 74 minus 34, which gives us a number of neutrons of 40. Our number of electrons is just equal to the number of protons minus the charge, which in turn gives us, we have 34 protons, a charge of 0, and that gives us 34 electrons. Does this first part make sense? Do these calculations look familiar to everyone from chapter 2 on isotope notation? Perfect. So let's look at the next portion of this isotope notation review. So in this case, we're given that we have nitrogen 15, 3 minus. So we know that nitrogen, looking at our periodic table, what is our atomic number?
7.
Yep, exactly right. Nitrogen has an atomic number of 7. So for our number of protons, we'd have 7 protons. Thinking about our neutrons, we get our mass number minus the number of protons, which gives us a number of neutrons of 15 minus 7, which would be 8. Then for our number of electrons, we take the number of protons minus the charge, which gives us, for our number of electrons, 7 minus -3, which gives us 10 electrons. This example was from one of the note sets, actually. Does this example make sense? Any questions on this example? Okay, so let's clear this and let's look at this next case where we're asked to write the element symbol. So in this case, we know that our number of protons is equal to 23. So what element has an atomic number of 23? What element has an atomic number of 23?
I don't know the name, but the symbol is V.
Yep, that would be vanadium. Yep, perfect. As long as you can get the symbol, that's all you need for this isotope notation question. So now that we have the symbol established, okay, let's try to calculate the mass number that we need. So the mass number is equal to the number of protons plus the number of neutrons. That in turn gives us a mass number of 23 plus 28, which gives us a mass number of 51. For our charge, we're going to take the number of protons minus the number of electrons, and that gives us a charge of 23 minus 18, or plus 5. So we'd write our symbol, our mass number, our atomic number, and then our charge. So this would be a complete symbol for this following vanadium isotope. Does that make sense?
Professor, when they are ions, so should
Yeah.
we put the charge on it for the symbol? Should we put V5 plus or just V?
V5 plus.
Okay.
Mhm. Or plus 5. Either is fine.
Either one.
Mhm. Wonderful. So let's look at this next example where we have mercury 2 plus. So first things first, we need to look up mercury in the periodic table. And what is the atomic number for mercury? What is the atomic number for mercury?
80.
Yep. Okay, so we know that our number of protons is equal to 80. Our number of neutrons is equal to the mass number minus the number of protons. So for our number of neutrons, we have a mass number of 202 minus 80 protons. That gives us 102 neutrons. Now for our number of electrons. Our number of electrons is equal to the number of protons minus the charge. So our number of electrons in this case would be 80 protons minus 2, which gives us 78. So we'd fill in the following numbers into the blank. Does that make sense? Any questions on this example? Okay, so let's keep going then. And if you have any questions at all, don't be shy to ask. This review is really to help everyone be comfortable with the content and to get any questions that you have addressed. So in the next case, we're asked to assume that we have an ion with a +1 charge. So now that we're given that the charge is provided, we know that our number of neutrons is equal to 21. Our number of electrons is equal to 18. Our number of protons is equal to the number of electrons plus the charge. That gives us, for our number of protons, we have 18 plus 1, or 19 protons. Okay, from our number of protons, we can look up in our periodic table, and what element has 19 protons? What element?
Potassium.
Yep, exactly right. And now we can calculate our mass number, which is equal to the number of protons plus the number of neutrons. And that in turn gives us a mass number of 19 plus 21, or 40. So this would be potassium 40 over 19 plus 1. Does this make sense to everyone? Any questions on this example? Okay, let's keep going now. And let's talk about this next example. In this case, we're asked to assume that we have an ion with a -1 charge. Okay, so with that information in mind, just like before, we know that our number of electrons is 54. We can figure out our number of protons by taking our number of electrons plus the charge. That gives us, for our number of protons, we have 54 minus 1, which is 53. Would someone like to tell me what element has an atomic symbol of 53? Oh, sorry, which element has an atomic number of 53?
Iodine.
Iodine, exactly right. Okay, so now that we have our number of protons and electrons, we can figure out our mass number. So let's execute on that idea. So the mass number is equal to the number of protons plus the number of neutrons. And that gives us a mass number of 53 plus 73, which is 126. So this is iodine 126, 53 minus. Does that make sense to everyone? Does this example make sense to everyone? Any questions on this example? Okay, so let's keep going with this. So we've completed the isotope notation problems. So let's identify, are the following species isotopes, ions, allotropes, or different element? So we have two samples with different formulas for the same element. What do we call that? Same element, but different formulas. What do we call that?
The allotrope.
Yep, exactly right. So these would be considered allotropes. Does that make sense? Okay, so let's keep going with this. So we're asked, are the following species isotopes, ions, allotropes, or different elements? So first and foremost, we notice that the atomic number is different and the mass number is the same. So if the atomic number is different, what does that tell us? Are these the same element or different elements?
They're different elements.
Yep, exactly right. So we just check the different elements box. Does that make sense? Perfect. So let's look at the next example. We're asked, are the following species isotopes, ions, allotropes, or different elements? So first thing we notice that we have a different charge. Okay. We notice that it's the same element. And we notice that they have a different mass number. So if we have different mass numbers, what does that tell us? If they have different mass numbers, what does that tell us? Same element, different mass number. What does that mean? What do we
Means they're
call it?
isotopes.
Isotopes, yep. And if we have the same element, but a different charge, what do we call that? Same element, different charge.
They're ions.
Yep, So these would be isotopes and ions. Does that make sense? Okay, so let's keep going with this. In this case, we're given that an element has 2 naturally occurring isotopes. So what I'm going to do is I'm going to copy this text and I'm going to share a whiteboard. Can everyone see the whiteboard that I've written? Can everyone see the whiteboard just to make sure?
Yes, we can.
Okay, perfect. So an element has 2 naturally occurring isotopes. Isotope 1 has a mass of this and an abundance of 80%. Isotope 2 has a mass of this. We're asked, what is the percent abundance of the second isotope? Well, we know that the percent abundance of isotope 1 and isotope 2, so all of our naturally occurring isotopes, should add to 100%. Ergo, the percent abundance of isotope 2 would be 100% minus the percent abundance of isotope 1, which would be 100% minus 80.00%, which gives us a percent abundance for isotope 2 of 20.00%. Does this make sense to everyone? Okay, perfect. So let's look back at the exam and let's tackle the next part of this multi-part question. So we're next asked to calculate the atomic mass of our element. Don't worry, we actually have enough information here. So I shared the whiteboard once again, and let's write all of the data that we have. Let's write all of the data that we have. So we know that the percent abundance of isotope 1 is 80.00%, and the mass of isotope 1 is 11.0093 AMU. We also know the percent abundance of isotope 2 is 20.00%, and the mass of isotope 2 is 10.0129 AMU. So then, if we want to calculate the average atomic mass, we take the percentage of isotope 1 over 100% times the mass of isotope 1 plus the percentage of isotope 2 over 100% times the mass of isotope 2. Punching that into our calculator, we have 11.0093 times 0.8 plus 20.00 over 100 times 10.0129. And that gives us an average atomic mass of 10.81 AMU. What element has an atomic mass of about 10.81? What element does that correspond to? What element has an atomic mass of 10.81?
Boron?
Yep, exactly right. Perfect. Does this example make sense to everyone?
Yes.
Perfect. So let's go back to opening up the exam. So let's look at this question. Question 33 is a really important concept. So if you sampled a single atom of the element, would the mass of that element match the mass found in the periodic table? So the mass in the periodic table, for example, for boron, this mass is known as the average atomic mass. So if we have an average atomic mass, will that match the mass of an individual isotope? Will that mass match the mass of an individual isotope?
No.
It wouldn't, right? It wouldn't. By definition, an average will be different from the two numbers that you average together, right? Just inherently. For example, if I have 1 and 3, my average will be different from these two numbers. It would be 2, right? Same principle applies. The average atomic mass doesn't match the mass of any given isotope. It's the weighted average of all elements and all isotopes of that element, all isotopes of that element, accounting for percent abundance. Does that make sense to everyone? Does this idea make sense?
Yes.
Okay, perfect. So let's keep going with this. So in this case, we're asked to measure the volumes, and this is where students often got a little bit stuck from a burette. Does anyone notice something odd about a burette? When we talked about burettes in class, what's the key feature of them?
0 is
So
on the
it
top.
goes-
Yep, they're upside down, exactly. Exactly. They measure from 0 to 50 from top to bottom. Okay, so now if we're asked to measure the volume of liquid in the burette, and we're asked to measure the initial volume and final volume, first things first, I need to figure out the value of a tick. So to go from 15 to 16 milliliters, it takes me 10 ticks. So we know 1 milliliter is 10 ticks. So then 1 tick is equal to 1/10 of a mil, and we can report up to 1/10 of a tick, 1/10 of the smallest graduated mark, which would be 1 over 100 milliliters, which would be 0. Oops.
Hello?
I think he accidentally got kicked out.
Oh, okay. I thought it was me.
Is anyone in here? Oh yeah.
What was that?
I was just wondering if I was the only one waiting still.
Yeah, I'm waiting to. I don't know, just to stay here. Maybe he'll be back.
Yeah.
I just messaged
I
him
guess
in
I'll wait a couple more
inbox.
minutes.
I just messaged him in inbox, see if he can respond.
Oh, okay, thank you.
Sure. I asked him if we should get out and log back in or what should we do?
Cool. Thank you.
Okay, so I'm waiting for the answer. How did you guys do on the exam?
I didn't do so well. I got a 65.
I made a mistake. I did it the last day and I just gave myself like 2.5 hours. That was a big mistake. So I didn't have time to do all those Lewis structure and everything.
Yeah, it was a lot. Those files that you had to turn in.
Uh-huh. Yeah.
Yeah, that took me forever. Oh my gosh. And then it was like little things like I thought transition metals were a part of like groups or like another type of group
Uh-huh.
because I know he said it was like group B or something, B through 8. So I
Uh-huh.
thought that like followed in line like with numbers 14, 15, and 16.
Mhm.
And I was like, oh, well, he's not really asking for just 8A or, 6A.
Uh-huh.
So like little mistakes like that. But it took forever. I was like exhausted. I was like, oh my
Yeah.
gosh. And I didn't even get like a really good grade. I was like, oh man, this is kind of discouraging.
Yeah.
I
I
don't
didn't
even
think
think
it
he
takes
graded
this
mine.
long.
Imagine if he had timed it. Oh my god, that would have been horrible.
So mine was
Yeah,
almost
there's
like
no way. I would have
fine.
there's no
Yeah.
way for me.
I made a big
I have a question. Would any of you would want to like do a group, like a study group? Because
Yeah.
like I'm struggling on the labs, and so I don't know if I think Jesse, would you like
Yeah, definitely. I'll send my phone number through
the chat?
the chat. So if anyone wants to start it.
Okay, sounds good.
Did you guys get an email? Like he said he's gonna continue the Zoom call through like a different meeting because he said he got kicked out.
Oh,
Did he send announcement?
No, it was like a separate email, like on the school email.
oh, school email. Okay.
Oh gosh.
In where?
And
Right?
yeah, he said he sent a new link to join.
Okay.
But where do you find it?
I think you just log into your school email and
Oh, a
then
school email. Okay. All right. Thank you.
Uh-oh. Okay, that's gonna take me a while. Shoot.
Oh, I got it. I'll see you guys over there.
Okay, bye.
Bye.
Professor? Ay, ay, ay.